like that. Are you seeing my presentation now, right?
Yes.
Good. Okay. Yes, I'm Bjørn-Helge Mevik. I've been working at UIO in the HPC groups there since 2008. I'm actually trained as a statistician. That's my profession before I started to work with computers here. And I've been working a lot with mainly queuing systems since I started here, and surrounding things that sort of comes into play in addition to that. But yeah, queuing systems is typically what I've been working a lot with, and setting them up on the different clusters and making sure they run fine and we have the setup we need. So today I'll talk about queue systems, obviously, and I'll sort of what they really are, because and so this is I'm going to try to be sort of more a conceptual lecture this, because there are some things that are very important to understand how a queuing system actually works and things in order to be able to make good decisions later on. So I will not present to you like a gazillion examples of how to run a job in this or that fashion. I will try to tell you the building blocks, the elements of this. That's my goal here. If I fail or not, that we'll see. So I'm going to first go very quickly, sort of on very general level of what a queue system is at all. Then I'll say a little bit more specifically about Slurm, and also inside there a little bit about how we have set it up, because it can be configured in many ways. I'll talk a little bit about best practices, things that you should think of, that's not necessarily obvious when you start working with queue systems. So that's the do try this at home section. And finally, very, very briefly about the different job types. As I know I showed you, we have quite a different range of computer clusters, and with them comes a quite wide range of different job types, and they have different characteristics, they have different usages and limitations and stuff. And if I were to sort of present all of them in all the combinations and tell you how to run them, we would be sitting here for the rest of the day. So I will keep that at a very sort of basic level and overall guidelines. Okay, so first, what is a queue system? And if you've been working with queue systems a long while and think that this is you basically know all this, feel free to let your mind wander, but come back in a couple of minutes when we go back over to Slurm. As Olivia told me yesterday, that's a good picture. On an interactive machine where you just log in and do stuff, you can think of that as a salad buffet in a restaurant where or in a place where everybody just goes up to the counter and takes what he wants here and there, and you just line up for there, and you have to wait for the eggs because they run out and stuff. It's completely organized, but people tend to work together well, and you get what's there and you see what's used and not. A queue system is sort of the completely opposite range of restaurants. You can think of the queue system as the guy, the head waiter showing you to your table. You line up in front of the restaurant. That's the job queue. He will then, when there are free seats at the table or free tables, he will then lead you to the table, sit you down, and then get you a menu, and you can order, and you can get to eat and pay and leave. That's your jobs running. In some cases, there might be some people have been phoning up ahead and made a reservation of a table at 4 o'clock or whatever. That's future reservations. We have like one for this course, which is then this best practices reservation on Saga. That's one type of that. That's the really, really big global picture of what a queue system does. It takes jobs, puts them in a queue, and when there are idle resources to run them, it runs them. Simple as that, and as difficult as that. Little bit more in detail of these systems. There are some basic concepts that sort of are the same for all queues. First of all, that you have a machine with some machine resources that are available for jobs, memory, CPU, whatever. Then in order to be able to ask for something, you have to describe what you need. So what your job requires, you have to have a job description. Typically, we put that in the top of a job script. It could be put on the command line as well, but anyway, it has to be there. And then we write a job script, which is basically the program we want to run, in addition to maybe these requirements. We submit that to the job queue with a command. In Slurm, it's dispatch. In other commands is qsub or whatever, in all the queue systems. And then after a while, the queue system schedules the job, meaning it starts it on some node or some nodes, typically by priority, but it doesn't have to be that. We usually use priority, but plus some extra stuff. Oops. Yeah. The machine resources that you have available on a machine, on a cluster, is what we call a node with resources, and it's not a really good name calling it a node. It's a computer, but I think it comes from graph theory and the first clusters of computers being seen as a network of computers, where a network is in a graph, and a graph has vertices, which is the network links, and the nodes are sort of the computer. So then the name stuck, and we just can't get rid of it. We, in our minds, we talk about compute nodes and login nodes and whatever. We mean machines, but we call them nodes. They consist of a number of CPUs, obviously, some RAM memory. Some of them have GPUs. Some of them, as I now told on Saga, have fast local disk. So not just this shared cluster file system, but some local disk you can ask for. In some cases, you even have different types of networks. In our cases, we don't have that, but earlier on, when we were running Titan, a local cluster at UIO, we had different types of networks depending on what you needed. There can also be things like software licenses. That's MATLAB has a license that you have to ask for you to be able to check out the license and so on. Let's see, yes. And the job requirements is basically you list up what you need of this, but not just what you need, but also in which configuration. So do you need 50 CPUs? Well, that's a bad number, nobody uses 64 CPUs, okay, but do you need it on one compute node, or couldn't they be anywhere, like 2 on this one and 16 on that and so on? And memory, do you need it sort of in certain configurations, or is it just that much memory per CPU? And also very important is how long do you need these resources? And we will see that can affect how fast your job is scheduled. If you ask for too short time in most configurations, your job will be killed when it's hit that time limit. So that's typically not a good idea. But if you ask for way too long, your job might never start because there won't be any free resources for you to start. And finally, there are accounting specifications, because at the top there are people that are buying these machines and financing them, and then they want to have some control over who runs how much. So they have an accounting system, and we use this project name and then the 4 digits and a K as the account, that sort of a bank account that jobs get accounted on, so that you get to run what you have been promised, but not more. That is it for the general high-level overview of queue system. So everybody who's wandered their minds to more pleasant things should probably now come back. Because now we're going to talk a little bit more about Slurm itself, which is more practical useful. Slurm is new-ish. It started in 2001, and the first version was in 2006. And in terms of queue system history, that's quite new. It's only, I mean, it's not 20 years since the first version 1 came out. So that's quite new. And that has the advantage that it came after computer nodes or machines tended to have lots of CPUs and cores on them. In the olden days, there was one machine and one CPU. Ole will arrest me because there were other machines as well. But for compute clusters, that was basically it. One machine, one compute, and one CPU. And also GPUs have been coming more and more, and other types of specialized hardware. So since Slurm is that new, it has been able to pull that in. Other queue systems do that as well, of course, but to various degrees. It's been quite popular. I think almost over half of the top 10 biggest known supercomputers in the world use Slurm. It's free. It's GPG license, so anybody can download it and run it, and then you can pay for support if you want. And it's reasonably fast running. Some of the old queues were extremely slow. They could take a couple of minutes just to go around and see which jobs could start now. And actively developed, at least if you pay for support. It has one feature. It has a single job queue. There is only one queue of jobs. You will probably hear, put it in a normal queue, or the big man queue, or the Axel queue, or whatever. There are no such things. There's just one job queue. Every job is in the same queue, and they have a priority. And in our setup, they are ordered by priority. So by default, they start by priority, and your job gets a higher priority the longer it stays in the queue. So everybody starts with the same priority as a default. And then if you waited 1 minute, you get 1 point more in priority, and so on and so on. But in addition, we also do backfill, because if the first job wants a lot of resources and it can't start now, then there might be a few resources here and there free for other jobs to start, and they will then start if they don't delay this one. You can see a picture of this here. At the top half, there is a 3-node machine we're thinking about. The green line there, vertical line, that's now. That's what it is. Each of these 3 nodes, have 4 CPUs, and you see there are 3 or 4 jobs already running. That's the red boxes. And they've started earlier, and they're currently running. And then there are 2 jobs in the queue. There's number E and F. And the idea is that E is the highest priority, F the next highest, and so on. So the queuing system can't start any of those now, but it will look forward in time and see, well, at time such and such, when job B finishes, I can start job E on the 3rd node. And when job D finishes, I can start job F on the 1st node. Fine. With backfilling, if we have new jobs that are smaller, shorter, and not too wide, like H and G here in the bottom level, they will be allowed to start now if they can, unless they come in the way of E and F. So they're not allowed to push E and F further out in time, because E and F have higher priority. But if they don't do that, they can start now. This fills up lots of gaps and utilizes the machine in a much better fashion. This is why we say, if you know that your job finishes in 10 hours, don't ask for 7 days. Because like the G job here, they would be so long that it would have delayed the F job, and it wouldn't be allowed to start. Well, they could start on node 2, so that was a bad example. But let's say the H job, it wouldn't have been allowed to start. That's what I think I'm going to say about backfilling. Let's see, how am I on time? I think I'm quite good on time. I'm not. I've got. I think I've got 40 minutes. I haven't planned to use that much time, but sometimes I just wander off, and then time run away. I'm going to show you what I believe is the most important slide in this deck of slides. Is what I've called the anatomy of a Slurm job. How is a Slurm job built up? And the reason this is important is that all documentation and error messages and outputs and everything will be in terms of these concepts. We'll see an example on the next page to make it more concrete. First of all, a job is the job as a whole. You know, the job script you've written, the priority it has in the queuing system, the requirements, and so on. That's the whole job. And then Slurm divides a job into steps when it starts to run. It starts first with a batch script. It executes that, and that counts as a step. And then every time you have NPI run or srun inside the job to fire off another processes then in parallel, typical, that is a new job step. And finally, each of these steps are divided into tasks. That's the processes. So if you ask for a node with 40 CPUs and want to run 40 tasks, you say you ask for any task equals 40, and then you start NPI run or srun in there. And they will then start 40 processes for you. And that's the 40 tasks of that step. So it's a job, and then sequentially job steps, and in parallel, those job steps have tasks. People used to programming in MPI will call these ranks. That's the name they use there. So it's the same thing. I'll show it in practice, so it might be easier to understand it. A small example, very, very small job, call it test job, run it in my account. I ask for 4 tasks and 500 megabyte of RAM per CPU. One task per default has 1 CPU. If you don't ask for anything else, you get 1 CPU per task. And then the memory is that, say, okay, every task needs 500 megabyte. It's allowed to run for 10 minutes. I just load an NPI module, and then I start a first step, or what Slurm calls step 0. That's the first NPI run or srun command there. I just run hostname init. And then I start the next step, which is then I've specifically asked it not to start more than 2 tasks in this case, just for fun in this case. But it will be a second step. And if you later run sact, or if you look at what currently is at the end of all output files in our setup, you will see lines that something like that at the bottom here. And they present 1 line for each step. First, there is 1 for the whole job as such. In this case, it's not very interesting because it doesn't say anything about the resources, but you can give a lot of options to get specific information like allocation, how many CPUs did you get, how much memory did you ask for, and so on. What was the runtime? And then the first line will be a good summary of the whole job. Then you get a line for the batch script itself, so which is the special step here. And typically you either just run a command there, and then that will be your main step, or you use srun or NPI run, and then you typically just use the batch script for a step for preparing stuff, compiling whatever, copying files and stuff, and then the main computation will be done in NPI run or srun steps. You will also see there is a very special external step here, which we don't really need to bother about now. It's some artificial thing that Slurm sets up for you, and it doesn't take any resources or whatever. It starts when the job starts, ends when the job ends. And it's only used if you SSH into a compute node where we have a running job. Then your processes end in that external step. So it can mostly be ignored. Now then, going back to, no, sorry. that is the how Slurm thinks of a job. Now, how does that affect how we specify resources when we want to submit jobs? Well, this is in general because not all clusters are set up alike, so there will be differences between the clusters. But in general, we specify the tasks we need, the number of tasks, how they are allocated across nodes, and we specify how much resources each task need. So typically you would use n tasks or n tasks per node or node to specify how many tasks. On Saga, I typically recommend using n tasks. So say I want 15 tasks, which means 15 processes. And then you specify how much resources each task needs. You can say CPUs per task. If you're running a multi-threaded job, that's the way to do that. By default, it's 1. So if you omit CPUs per task, you get 1 CPU per task. But if you have like you want to run 16 processes in your tasks, either 1 task or more, then you say CPUs per task equals 16. Use that instead of n tasks per node, instead of n tasks, I'm sorry, because with CPUs per task, you are guaranteed that these 16, or whatever you ask for, CPUs are on the same compute node, because threaded applications have to have all their threads on one machine. That's how threads work. You can start a process on one machine and another process on another machine, but a single process must have all its threads on one machine. That's just how computing works. And then typically you would ask for how much memory you want per CPU. For some reason, they haven't decided to say mem per task in Slurm. I don't really know why, but that's how they do it. So if you have a multi-threaded task, then you would have to account for that, so that the mem per CPU times the number of CPUs is the amount of memory you need for that task. GPUs are a little bit different because they are sort of on the sideline here. They are called general resources in Slurm, and they are not built up in this way. So those are specified directly. You say how many GPUs you want, typically minus GPUs or GPUs per node. One should have been able to use GPUs per task, which had fitted very well into this setup. But currently there is a bug in Slurm, in the current version of Slurm, the one that we have at least, that makes this doesn't work. Your job will be accounted for a lot more than it should be, and I think on Saga it won't even start. So currently we can't use that, unfortunately. Hopefully that will be fixed in a while. Finally, time, sort of the fourth dimension in the word there, specified by minus time. And then of course there are all these special things like licenses and as I now mentioned, these local Scratch file systems. I haven't put all of those up here. They are documented in the online documentation. But I do encourage you to use local Scratch when you need it, because it not only makes your job go much faster, it also makes everybody else's job go faster, because if you try to run very IO intensive jobs on the cluster file system, even though it's a very expensive high performance file system, if you get enough of those jobs, it'll slow it down really. But the local file system will be very few people on the same file system as you, and it's even faster. So use that if you have high IO needs. Finally, I think from the part of the Slurm setup here is how we do accounting in NRIS. And notice that this is for NRIS specifically. Other clusters you will find if you go around and work at other places will do things differently. We account in terms of what we call a billing unit. It's calculated from the CPUs you ask for, the GPUs and RAM. So a CPU has a cost of 1, RAM has some cost per gigabyte, and GPU some cost per GPU. And then it just says, okay, If you ask for 5 CPUs, that's 5 points. If you ask for 2 GPUs, that's so many points. And if you ask for that much RAM, you get that many points. And it takes the biggest number. So if you, and we try to balance it. So if you take all the GPUs on a compute node, which is 4, actually I can't remember if it's 2 or 4 on Saga. Anyway, let's say it's 4. You take all the 4 GPUs on a compute node on Saga, that will cost as much as taking all the CPUs. We try to balance it that way, and the same with memory. The details are at this page here, and if you download the PDF, I think it's a clickable link, so you don't have to type the link in. You can also see a job after it finishes, how many billing units did it actually cost by using this exact command. It's exact with your job ID, and it specifies the outputs job ID and alloc tres. This magic %40 characters is just because by default exact will just truncate the result, and that's not very useful for us. So giving it 40 space, a wide space of 40 is probably good enough. And then I've added elapsed as well to see how long it actually ran. And then you will see billing equals something, 32 for instance, and then elapsed this many hours. And then you can just multiply, and you know how many billing hours this job cost you. You can get the billing information also from scontrol show job, but that's only while the job is running. And you can also get an overview of your total usage in your project by the cost command, as I'm sure you're aware of. And you will see both in when we talk and when we write documentation, we tend to say CPU hours instead of billing hours. It's just, it used to be CPU hours, and that's so much easier to say, and everybody heard about it. So when we say or write CPU hours, it is billing hours we mean, but yeah. That was the last part for the sort of our Slurm setup and how Slurm works. I'll just go back and say again, these concepts are job, step, and task. Get a grip and understanding of what they are, and get used to them, and your life will be much easier on a Slurm cluster. Then I have 2 slides about best practices, what to do and what not to do. There are general guidelines, and they don't always, you can't follow them without thinking yourself. Maybe the best practice first should be think, but that's a bit arrogant, so why not? First of all, don't specify way too much longer time than you need. It's a good practice to specify somewhat longer than you have found that your code at optimum takes. There might be delays. Somebody might be slowing down the queuing, the file system, and while you do reads and writes and stuff like that. So give it a little leeway, but not far too much. Because as we saw with the backfill thing, you will not be able to get the job backfilled if you do. And at the same time, in a similar way, don't ask for more CPUs and more memory than the job really needs. It wastes resources. Specifying a too long time doesn't really waste resources, because when your job is actually finished, it exits and another one can start. It just gets your job later scheduled. But specifying like, I want a whole node, and then you run 1 CPU and use 5 GB of RAM, that's wasting a lot of CPUs and RAM that other people could have used, or your own other jobs could use. So first of all, that's wasteful, and compute clusters are in high demand, so don't waste it. Also, you will be accounted for all you ask for in terms of memory and CPU, no matter how little you actually use, because you prevented other jobs from using it, so your job will take the cost. And also, if you don't need all your tasks to be running on a single node, then don't ask for that, because it might be easy for the queuing system to find 40 CPUs available here and there on the compute, on the cluster, than finding a whole node with 40 CPUs idle right now. which means that your job will start soon. Of course, some jobs really do take advantage of having all the processes on the same nodes, especially if they do a lot of communication between the processes. That will always be faster than the network, even though we have quite a fast InfiniBand network. So sometimes your job will benefit from having everything on the same node, so that you use n tasks per node when you specify the job. That can give shorter runtime. Unfortunately, will often give a longer queue time. So what should you optimize for? Well, I'd say look at the situation. If you log in and see that you put it in the queue system and see that there are lots of idle resources, lots of machines idle, then of course you can optimize your job for the fastest runtime. Not only will it run faster, it will eat up less billing hours from your account. Very good. On the other hand, if there is a long queue and you don't have infinite number of time waiting for your results, then it's better probably to optimize for shorter queue time by just specifying n tasks. Then your job will run longer, maybe, but it'll probably start much sooner. So there is no possibility to give sort of this is always better than that. It depends on the load, and that can vary between days. Second of the best practices, in general, on Saga at least, I would say use n tasks if instead of n tasks per node as a start there. If you see that your job runs much slower, then consider using n tasks per node instead. But it will start sooner, and it is easier to fill up the holes in the cluster that way. And when you want to have run a multi-threaded program, use CPUs per task. Don't use n tasks, because then you might get CPUs on different compute nodes, and your process will run its threads on the same computer anyway, so you won't be using the other the other CPUs. I would also say use mem per CPU. It is possible to use mem instead to ask for memory, but mem says I want this much memory on every compute node that my job lands on. And if you haven't specified exactly how your processes will land on compute nodes, you might get all your tasks on one compute node, or you get one task on each compute node. And then you still ask for like 100 gigabyte on each of the compute nodes, which is wasting a lot of memory, or even the other way around. In total, you might need more than 100 gig if everything ends up on one compute node. So use mem per CPU, at least on Saga. That's my recommendation. And finally, don't use exclusive. If you think you need to use exclusive, ask us. Exclusive does some things that you don't really want. If you want to run on a node by yourself, just specify enough memory or CPUs so that you take the whole node. You could use mem equals 0, for instance, and take the whole node. But then remember to specify so that all your processes actually end up on the same node. Otherwise, you're wasting resources. But don't use exclusive. It really doesn't work well with our setup. Finally, one little slide about the job types, because it was part of the title of the talk I discovered after a while. We have a list of all the job types at this URL, choosing job types, and lists is an overview of the different job types of the different clusters and their characteristics, their how to specify them, and their limits, and so on. And the different clusters have different job types. All of them have the normal jobs, but they're not the same on Saga as on Fram. they have different. On Fram, you get whole nodes. On Saga, you get CPU plus memory, right? All of them have a development type of job that they can use for testing stuff, not for production, but when you sort of, I want to test if this code runs, you check it there and you get results immediately, hopefully, and then you can go on. Some of them have big mem for large memory applications, Axel for GPU nodes, and so on. And do read this page and the descriptions of them, and select the job type that fits what your job wants to do and what they are meant for. Especially don't use Devil to run jobs to get higher priority. Devil is meant for the typical case where you submit one job, you sit at the keyboard and wait for the results to be done and see how it went, and then you do some modification, fix your code, whatever, try another compilation option, whatever, and you just submit a new Devil job. You sit at the keyboard and wait for the results. It is not meant for sending in 10 or 20 jobs and waiting for all of them to finish and figure out what's what. That's not development in how we sort of set this up. And it's not to be, this is not to be mean. I mean, we could create development queue or job type that everybody could run, and you can run as much as you wanted. But then everybody would run there, and then everybody would get higher priority, and jobs wouldn't start faster anyway. So we have to limit how much can be run in the development queue for it to actually have an effect as a development queue. So don't abuse it. Don't use it in scripts or in setups where you submit a lot of jobs. That's not what it's for. It will be typically some other user or we will notice, and someone will get angry, and yeah. So don't do that. I think this was it. Yes. So I think we are all about just right on time. And yes. Maybe if there are questions so directly, I don't know.
Yeah.
So Bjørn-Helge,
yes.
Daniel, how long do we have now for the next session?
You can take 5 minutes questions every. We can take a 10 minutes break later.
So thank you, Bjørn-Helge. So it's very eye-opening description of certain things, how to look at it. If I can ask few questions about sometimes when we use scontrol command, for example, there are so many things that Slurm prints tells us about the job status. So there are terms like quality of service, priority, and requeue, and that sort of. So this information, how do we sort of interpret it? Do we need to understand this to understand why our job is late, or do you have any comments about that?
For understanding why a job is late or sort of hasn't started yet, there is basically one field that is the most important, and that's the reason. It's a field called reason, and it'll print a symbolic name of why the job hasn't started yet. And that's probably most important. It could be things like dependency, which means that you've specified that this job should run after somebody else, some other of your jobs have finished or something. Or it could be priority, meaning that it's waiting in line, but there are higher priority jobs waiting to start. It could be resources, meaning that this is the top priority job, but there aren't any idle resources right now. Or it could be typically you don't have enough billing hours. It's ASOC group billing mins, I think is a very strange name. But if you see billing in billing mins in there, it means you don't have enough CPU quota or CPU hours left on your quota. So that's the most important there. But of course, looking at it and seeing that the other things like the partition and stuff matches what you wanted to specify is also good to check for errors or see for, because maybe you intended to run the Devil job, but you forgot -q Devil, and then the QS will be normal instead of or it will be your project name. Anyway, it will not be QS Devil, right? So looking at some of these things that match the specifications you have is also a good idea. To see when I specify these, how much resources does it actually get? There is this building tress thingy in there that you also can get from exact, and that should sort of match what you think you've specified. Because sometimes you, in a job script, you write a lot of things and you comment something out, you put 2 hashes instead of 1 in front, and suddenly you've forgotten that 1 is out, and you overlook that, and you haven't specified what you think you have specified. But there is a lot of other things, like which node this was submitted from, and a lot of other stuff there that is not very important to know.
So in your that beautiful plot that you showed how the jobs are queued, is there a way to explain this eligibility time and submit time and start time, occurred time? So there are several time units are there.
Yes, the submit time is simply when you ran SBatch or SLOC if you have an interactive job. That's exactly that time. But in some cases, you yourself or some other circumstance makes it possible that this job is not ready to run now. You can actually say minus begin time and then something else. Then you specify this job should not start before that. This is the eligible time. It will show when the job was ready to run. For, I think, most jobs, it will be the same as the submit time. And sometimes when a job is re-queued, it will not start it until a couple of minutes later, just to avoid endless loops of jobs being re-queued for some reason. And then you will see that the eligible time is actually 2 minutes after the last submit time. And then start time is, of course, when it actually did start. And I think it's end time when it finished.
Okay, thank you, Bjørn-Helge. And I have one question regarding this billing. I always thought that a user is billed for what they are used, not what they asked for. But did you tell that the users are supposed to pay what they asked for?
In terms of CPU and memory and GPUs, yes. But in terms of job time, it is what they use. Because if you ask for 40 CPUs, then Slurm will make sure that you get 40 CPUs that nobody else can use. And that is why we say that no matter if you just run one single CPU there or you actually use all of those 40, you will have to pay for all of them. You get billed for all of them because you're preventing others from using it. Time is a little bit different because, yes, if you specify a very long wall time, when your job finishes, like after an hour, or maybe it crashes after half an hour, who knows, it happens, then those resources are free for everybody else to use. So you won't get charged for things that after your job finished. So it's just the sort of, if you look at time on a horizontal scale and your resources vertical, it's the vertical part that you get billed for what you ask for, and not what you use. So okay. Yeah.
That's new information for me. It's good. Thank you. And is there any questions on HackMD which is not needed to be answered here, discussed here, Sabri or the other one? No, I didn't see anything. And I just request all of you to ask questions on this collaborative document so that we could discuss it or either answer it. Thank you so much, Bjørn-Helge. This was very informative to me, and I hope it was everything same for everyone else.
I hope so.
Thank you.